What if I told you that somewhere in the vast expanse of the universe, there are signals so powerful they can outshine entire galaxies, yet they last just milliseconds and vanish without a trace? These cosmic enigmas are known as fast radio bursts, or FRB, and they've left scientists scratching their heads for years. Picture this: a burst of radio waves traveling billions of light years across the cosmos, carrying with it secrets about the universe we can only begin to imagine. Yet, despite their fleeting nature, these signals have sparked a race to uncover their origins. Are they the result of colliding neutron stars, the cries of dying black holes, or perhaps something even more extraordinary? In this video, we're diving deep into 50 mysteries surrounding FRB's mysteries that challenge our understanding of the universe and push the boundaries of science itself. From their mind-boggling energy to their unpredictable behavior, each mystery is a puzzle waiting to be solved. So, buckle up and get ready to explore the unexplained. By the end of this journey, you'll not only have a clearer picture of what FRBs are, but also why they remain one of the most fascinating cosmic phenomena in the universe. Stay tuned, because this is one mystery you won't want to miss. Now, shifting our focus to the very beginning of this cosmic mystery, let's rewind to the year 2007, when the story of fast radio bursts first unfolded. It was at the Parkes Observatory in Australia, a facility renowned for its contributions to radio astronomy, that scientists stumbled upon something extraordinary. While sifting through archival data from the telescope, they detected a brief, intense burst of radio waves that lasted no more than a few milliseconds. At first, it seemed like nothing more than an anomaly, a glitch in the data, or perhaps interference from Earth. But as more observations were made, it became clear that this signal was anything but ordinary. The burst, now known as the Lorimer burst, originated from deep space, billions of light years away. The discovery sent shockwaves through the scientific community, sparking both excitement and confusion. What could produce such a powerful signal in such a short amount of time? Theories began to swirl, but answers were elusive. This singular event marked the beginning of a new chapter in astronomy, one that would challenge our understanding of the universe. And so, the hunt for more fast radio bursts began, with the Parkes Observatory at the forefront of this groundbreaking research. Now, turning to another fascinating chapter in the story of fast radio bursts, we encounter a discovery that deepened the mystery even further. In the year 2012, scientists detected something unprecedented, a fast radio burst that didn't just flash once but repeated itself. This burst, named FRB 121102, was the first of its kind, shattering the assumption that all FRBs were one-time events. Located in a dwarf galaxy nearly 3 billion light-years away, this repeating burst sent out multiple signals over time, allowing astronomers to study it in greater detail. But its repeating nature raised more questions than answers. Why do some FRBs repeat while others vanish after a single burst? One theory suggests that repeating FRBs might originate from highly energetic objects like magnetars, which are neutron stars with incredibly strong magnetic fields. These objects could produce bursts sporadically, explaining the repetition. On the other hand, non-repeating FRBs might come from catastrophic, one-time events, such as the collision of neutron stars or the collapse of a massive star. The discovery of FRB 121102 not only expanded our understanding of these cosmic signals, but also highlighted the vast diversity in their origins. As researchers continue to study repeating FRBs, they hope to uncover more clues about the mechanisms behind these enigmatic phenomena, and perhaps solve the puzzle of why some repeat while others do not. As we venture deeper into the mysteries of fast radio bursts, a central question emerges: where do these powerful signals come from? The origin of FRBs has sparked intense debate among astronomers, with several leading theories vying for attention. One of the most widely discussed possibilities is that FRBs are emitted by neutron stars. The the dense remnants of massive stars that have exploded as supernova. Neutron stars are known for their extreme conditions, including intense magnetic fields and rapid rotation, which could provide the energy needed to produce such bursts. Particularly magnetars, a type of neutron star with an extraordinarily strong magnetic field, are considered prime candidates. These objects can unleash massive amounts of energy in a split second, potentially explaining the brief but intense nature of FRBs. However, not all FRBs fit neatly into this explanation. Some scientists propose that black holes, especially those in the process of devouring matter or merging with other black holes, could also generate these bursts. The immense gravitational forces and chaotic environments around black holes might create the right conditions for FRBs to occur. Yet, there's another intriguing possibility. What if FRBs come from something entirely unexpected? Some hypotheses suggest exotic objects like quark stars, theoretical remnants even denser than neutron stars, or even cosmic phenomena we haven't yet discovered. The diversity of FRB properties, such as their repetition, energy, and distance, hints that there might not be a single origin. Instead, multiple sources could be responsible, each contributing to the cosmic symphony of these mysterious signals. As researchers gather more data, the puzzle of FRB origins continues to evolve, reminding us just how much we still have to learn about the universe. Now, shifting our focus to the vast expanse of the cosmos, let's explore the mystery of how far these fast radio bursts actually travel. Measuring the distance to FRBs is no small feat, but scientists have developed clever methods to tackle this challenge. One of the key techniques involves analyzing something called dispersion, which is essentially the spreading out of the radio waves as they travel through space. Intergalactic space isn't empty, it's filled with a thin plasma of free electrons. When FRB signals pass through this plasma, their higher frequencies arrive slightly earlier than the lower ones. By measuring this delay, scientists can determine how much material the signal has traveled through, and from there, estimate its distance. This method has revealed that some FRBs originate from mind-bogglingly distant locations, billions of light-years away. But why are some FRBs so far away? This distance tells us that FRBs are not just local cosmic events, but instead occur in galaxies across the universe. These remote signals act like cosmic messengers, carrying information about the environments they've traveled through. For example, by studying the dispersion of these signals, scientists can map the distribution of matter in the universe, including the elusive cosmic web of galaxies, gas, and dark matter. The incredible distances also hint at the power of FRBs. To be detectable from billions of light-years away, these bursts must release an enormous amount of energy in just milliseconds. This raises even more questions about what process could produce such a tremendous outburst. As we continue to detect more FRBs and refine our methods for measuring their distances, each new discovery brings us closer to understanding not just the bursts themselves, but also the structure and evolution of the universe on the grandest scale. Now turning to the astonishing power behind these cosmic signals, we delve into the mystery of the energy released by fast radio bursts. Imagine this: in just a fraction of a second, an FRB can unleash more energy than the sun produces in several days. This astonishing intensity raises a fundamental question: how can something so brief outshine entire galaxies? The sheer scale of energy involved is hard to comprehend. For instance, one of the brightest FRBs ever detected released energy equivalent to hundreds of millions of suns, all in a matter of milliseconds. To put this into perspective, if you could harness that energy, it would power Earth for billions of years. But what cosmic event could generate such a colossal outburst? Scientists have proposed several theories. One leading idea suggests that magnetars, highly magnetic neutron stars, could be responsible. When these stars experience sudden magnetic field shifts or starquakes, they might release energy in the form of FRBs. Another theory points to cataclysmic events like black hole collisions or neutron star mergers, which could produce bursts of energy intense enough to match what we observe. The challenge lies in pinpointing the exact mechanism, as these events occur far beyond our ability to observe directly. What we do know is that the energy released by FRBs provides a unique window into some of the most extreme processes in the universe. By studying these bursts, we gain insights into the behavior of matter and energy under conditions that are impossible to recreate on Earth. Each new FRB detection brings us closer to unraveling the origins of these energetic phenomena, offering clues to not just the bursts themselves, but also the nature of the cosmos at its most extreme. Now shifting our focus to one of the most compelling theories in the study of fast radio bursts, we examine the role of magnetars. Magnetars are neutron stars with magnetic fields so incredibly strong that they dwarf anything we find on Earth. To put it simply, their magnetic fields can be up to 1,000 trillion times more powerful than Earth's. This immense magnetic energy makes them prime candidates for generating FRBs. The idea is that when a magnetar experiences a sudden disruption, like a starquake or a massive shift in its magnetic field, it could release a burst of energy in the form of an FRB. This process is not just theoretical, there's growing evidence to support it. In April 2020, scientists detected an FRB originating from a known magnetar in our own galaxy. This was a groundbreaking moment because it provided the first direct link between magnetars and FRBs. The burst matched the characteristics of extragalactic FRBs, suggesting that similar processes could be at work across the universe. Additionally, the timing and energy of the burst aligned with what scientists would expect from a magnetar event. However, not all FRBs can be explained by magnetars alone. Some bursts are far more energetic than what magnetars are thought to produce, hinting that other cosmic phenomena might also be at play. Still, magnetars remain a key piece of the puzzle, offering a plausible explanation for at least a subset of these mysterious signals. By studying these highly magnetized stars, we gain valuable insights into the extreme conditions that could give rise to FRBs. The connection between magnetars and FRBs continues to be an active area of research, with each new discovery bringing us closer to understanding these enigmatic cosmic bursts. Now turning to the majority of fast radio bursts, we encounter a fascinating distinction: the non-repeating FRBs. Unlike their repeating counterparts, these bursts are one-time events, flashing across the cosmos in milliseconds and never appearing again. This fleeting nature makes them even more challenging to study. So, what sets them apart? For starters, non-repeating FRBs tend to release significantly more energy in a single burst compared to repeaters. This has led scientists to speculate that their origins might be fundamentally different. One leading theory suggests that non-repeating FRBs could result from cataclysmic events, such as the collision of two neutron stars or the collapse of a massive star into a black hole. These events are so powerful and destructive that they might only produce a single, intense burst of energy. Another possibility is that non-repeating FRBs are caused by highly energetic processes within neutron stars, but ones that are so extreme they destroy the star or render it incapable of producing another burst. Interestingly, the environments where non-repeating FRBs are detected also seem to differ from those of repeaters. Many non-repeaters appear to originate from older, less active galaxies, hinting that their sources might be different in nature. While magnetars are a strong candidate for repeaters, the origins of non-repeating FRBs remain wide open. Could they be linked to entirely different cosmic phenomena, or are they simply the result of more extreme versions of processes we're already studying? The mystery deepens with each detection, urging scientists to dig deeper into the conditions that create these singular bursts. As research progresses, understanding non-repeating FRBs could offer a new window into some of the most violent and energetic events in the universe. As we delve into the next layer of the fast radio burst mystery, let's focus on a subtle yet powerful clue: polarization. Polarization refers to the orientation of light waves as they travel through space, and studying this property in FRBs can unlock secrets about their origins and the environments they pass through. When an FRB's light becomes polarized, it means the waves vibrate in a specific direction, and this can be influenced by magnetic fields or the material the signal encounters along its journey. By analyzing the polarization of FRBs, scientists can infer details about the magnetic fields surrounding their sources and the conditions of the space they traverse. For instance, some FRBs exhibit highly polarized signals, suggesting they originated in environments with intense magnetic fields, like those near neutron stars or black holes. Other FRBs show signs of depolarization, hinting that their signals traveled through dense clouds of plasma or gas which scrambled their polarization. One groundbreaking discovery came from observations of repeating FRBs, where changes in polarization over time provided clues about the dynamic magnetic environments around their sources. These findings have led researchers to theorize that repeating FRBs might originate from magnetars, whose powerful magnetic fields could explain the observed polarization patterns. On the other hand, non-repeating FRBs often show different polarization characteristics, further supporting the idea that their sources might be distinct. Polarization studies have also revealed that some FRBs travel through intergalactic space relatively undisturbed, while others pass through turbulent regions with strong magnetic fields. This information helps scientists map the cosmic environments that shape these signals and refine their theories about what causes them. While polarization offers a wealth of insights, it also raises new questions. For example, why do some FRBs exhibit circular polarization while others are linearly polarized? What can these differences tell us about the mechanisms that produce these bursts? As researchers continue to decode the polarization patterns of FRBs, they inch closer to unraveling the mysteries of these enigmatic cosmic signals, shedding light on the extreme events and environments that give rise to them. Shifting our focus to the cosmic neighborhoods where fast radio bursts originate, we uncover another layer of intrigue: the host galaxies. These galaxies, vast collections of stars, gas, and dust, serve as the birthplaces of FRBs, and studying them provides critical insights into the environments that give rise to these fleeting signals. When astronomers detect an FRB, one of their first priorities is to pinpoint its host galaxy. This is no easy task given the immense distances involved, but advancements in radio telescopes and precise localization techniques have made it possible. By identifying these galaxies, scientists can analyze their properties, such as their size, age, and star formation rates, to understand why FRBs emerge from certain regions of the universe. One striking discovery is that FRBs are found in a diverse range of galaxies. Some originate in large, spiral galaxies teeming with young stars and active star formation, while others emerge from smaller, irregular galaxies with less stellar activity. This diversity suggests that FRBs can arise in various cosmic environments, but it also raises questions about what specific conditions are necessary for their production. For instance, do FRBs prefer galaxies with high rates of stellar explosions, like supernova, or are they more likely to occur in galaxies with dense concentrations of neutron stars or black holes? Interestingly, some FRBs have been traced to galaxies that are surprisingly close to our own, while others come from galaxies billions of light years away. The distance to these host galaxies provides clues about the age of the universe when the FRBs occurred, allowing scientists to study how these phenomena have evolved over cosmic time. For example, an FRB detected from a distant galaxy might have been emitted when the universe was much younger, offering a glimpse into the early stages of cosmic history. On the other hand, FRBs from nearby galaxies give us a chance to study these events in greater detail, as their signals are less distorted by the vast expanses of space they traverse. Another fascinating aspect of host galaxies is their potential link to magnetars, highly magnetized neutron stars that are one of the leading candidates for FRB sources. Some host galaxies show signs of recent star formation, which aligns with the idea that magnetars, being young stellar remnants, could be responsible for FRBs. In these galaxies, the chaotic aftermath of stellar explosions might create the perfect conditions for magnetars to generate these powerful bursts. However, not all host galaxies fit this pattern, leaving room for other theories about the origins of FRBs. One particularly intriguing discovery is the association of certain FRBs with dwarf galaxies. These small, often chaotic galaxies are rich in star-forming activity and may harbor unique conditions that favor the production of FRBs. The compact nature of dwarf galaxies could amplify the effects of magnetic fields or stellar collisions, making them hotspots for these cosmic bursts. This connection has led researchers to speculate that FRBs might be more common in such environments, though further observations are needed to confirm this hypothesis. As we explore the host galaxies of FRBs, it becomes clear that these cosmic neighborhoods hold vital clues about the origins and mechanisms of these mysterious signals. By studying the properties of these galaxies, scientists can piece together the puzzle of what conditions are necessary to produce FRBs and why they occur in such a wide variety of cosmic settings. Each new discovery brings us closer to understanding the environments that give rise to these enigmatic bursts, shedding light on the extreme events that shape the universe. Now shifting our attention to the invisible threads that weave through the cosmos, we delve into the role of plasma in shaping fast radio bursts. Plasma, often referred to as the fourth state of matter, is a hot, ionized gas that fills vast regions of space. It plays a crucial role in how FRBs travel across the universe and how they appear when they reach our telescopes. When an FRB is emitted, it doesn't travel through empty space. It passes through this sea of charged particles, and that journey changes the signal in fascinating ways. One of the most significant effects of plasma on FRBs is something called dispersion. As an FRB travels through plasma, its higher frequencies move slightly faster than its lower frequencies. This causes the signal to spread out or disperse over time. By measuring this dispersion, scientists can estimate how much plasma the signal has passed through, giving them a clue about the density of matter between the FRB's source and Earth. This dispersion is like a cosmic fingerprint, revealing details about the vast stretches of space that these bursts traverse. But plasma doesn't just disperse FRBs, it can also polarize them. Polarization refers to the orientation of the radio waves as they travel. When an FRB passes through regions with strong magnetic fields, such as those found in plasma clouds, its waves can become twisted or aligned in specific patterns. Analyzing this polarization can provide insights into the magnetic environments the signal encountered along its journey. For instance, if an FRB's polarization is highly twisted, it might suggest that the burst passed through a dense magnetized star-forming region. Another intriguing aspect of plasma's role is its ability to amplify or distort FRB signals. In some cases, plasma can act like a lens, bending and focusing the radio waves in ways that make the signal appear stronger or more complex when it reaches Earth. This phenomenon, known as scintillation, can create patterns in the FRB's signal that reveal information about the distribution of plasma in space. However, it can also make it more challenging for scientists to decode the original characteristics of the burst. Interestingly, the interaction between FRBs and plasma isn't just a one-way street. By studying how FRBs are affected by plasma, researchers can also learn more about the plasma itself. For example, the dispersion and polarization of FRBs can help map the distribution of plasma in galaxies and even in the vast voids between them. This makes FRBs not just mysterious signals to unravel, but also powerful tools for exploring the structure of the universe. As we continue to explore the role of plasma in FRBs, it's clear that this ionized gas is more than just a backdrop. It's an active participant in shaping the signals we detect. From dispersion and polarization to scintillation, plasma leaves its mark on every FRB, turning these bursts into cosmic messengers that carry stories of the environments they've traveled through. By unraveling these clues, scientists are not only solving the mystery of FRBs, but also uncovering new insights into the hidden fabric of the universe. Now stepping into the realm of the unseen rhythms of the cosmos, we explore the intriguing frequencies at which fast radio bursts are detected. These bursts don't just appear at random frequencies, they span a wide range from a few hundred megahertz to several gigahertz, each frequency carrying its own unique story. But why do some FRBs seem to favor specific frequencies? The answer lies in the complex interplay between their sources and the environments they travel through. At the lower end of the spectrum, FRBs around a few hundred megahertz are often more heavily affected by plasma dispersion, which can stretch and distort the signal. This means these bursts might appear more smeared out when they reach our telescopes, making them harder to detect and analyze. On the other hand, higher frequency FRBs up to a few gigahertz tend to cut through these distortions more cleanly, arriving at Earth with sharper, clearer signals. This difference in frequency can tell us a lot about the distance of the FRB and the density of the plasma it has traveled through. But frequency isn't just about the journey, it's also about the source. Some theories suggest that the specific frequencies of FRBs might be tied to the physical properties of their origins. For example, if an FRB is emitted by a neutron star, its rotation could influence the frequency of the burst. Rapidly spinning neutron stars might produce higher frequency bursts, while slower ones emit at lower frequencies. Similarly, the magnetic fields around these objects could also play a role, shaping the energy of the burst into specific frequency bands. Another fascinating possibility is that the frequencies of FRBs could be influenced by the environments where they originate. In regions with dense plasma or strong magnetic fields, certain frequencies might be amplified or suppressed, leading to bursts that appear more prominent at specific wavelengths. This could explain why some FRBs seem to cluster around particular frequencies, offering clues about the conditions in their host galaxies or even the immediate vicinity of their sources. Interestingly, the frequency range of FRBs also affects how we detect them. Radio telescopes are designed to pick up signals within specific frequency bands, and not all FRBs fall within the range of every telescope. This means that some bursts might go unnoticed unless we're looking in the right place at the right time and with the right equipment. As our technology advances, expanding the range of frequencies we can observe, we're likely to uncover even more of these elusive signals, painting a fuller picture of their diversity and origins. As we ponder the frequencies of FRBs, we're reminded that these bursts are more than just fleeting flashes in the cosmos. They're intricate signals shaped by their sources, their journeys, and the environments they pass through. Each frequency tells a piece of the puzzle, offering scientists another clue in the ongoing quest to unravel the mysteries of these enigmatic cosmic phenomena. Now shifting our gaze to one of the most puzzling aspects of fast radio bursts, we delve into their unpredictable timing. Unlike many cosmic phenomena that follow predictable patterns, like the regular pulses of pulsars or the cyclical nature of supernova, FRBs seem to appear entirely at random. This unpredictability has left scientists scratching their heads, wondering what could possibly trigger these brief yet powerful bursts of energy. One of the biggest challenges in studying FRBs is their sporadic nature. Most FRBs are detected only once, appearing as a fleeting flash in the vastness of space, never to be observed again. This makes it incredibly difficult to pinpoint their origins or understand the mechanisms behind their creation. Even the repeating FRBs, like FRB 121102, don't follow a strict schedule. Their bursts come in irregular intervals, adding another layer of mystery to their behavior. So, what could be causing this randomness? One theory suggests that FRBs might be linked to highly energetic but short-lived events, such as neutron star collisions or the cataclysmic deaths of massive stars. These events are inherently chaotic, making it difficult to predict when or where they might occur. Another possibility is that FRBs are produced by extreme magnetic activity on neutron stars known as magnetars. When these stars experience sudden shifts in their magnetic fields, they could release bursts of radio waves at seemingly random intervals. Another intriguing idea is that the timing of FRBs might be influenced by their environments. For example, if an FRB originates in a region densely populated with cosmic debris, the signal might be delayed or distorted as it passes through various obstacles. This could create the illusion of randomness even if the burst itself was triggered by a specific event. Similarly, the presence of strong gravitational fields, like those near black holes, could bend and scatter the signal, making it appear irregular when it reaches Earth. The unpredictability of FRBs also poses a significant challenge for astronomers trying to study them. Detecting these bursts requires a combination of luck and precision, as telescopes must be pointed in the right direction at the exact moment the burst occurs. To improve their chances, scientists are developing advanced detection systems and coordinating networks of telescopes across the globe. These efforts are slowly but steadily increasing the number of FRBs we can observe, bringing us closer to understanding their mysterious timing. As we continue to explore the enigmatic timing of FRBs, one thing becomes clear. These bursts are not just random flashes in the dark. They are the result of complex, high-energy processes that we are only beginning to comprehend. Each burst, whether it repeats or not, offers a unique opportunity to learn more about the extreme conditions that exist in the universe. And with every new detection, we move one step closer to unraveling the secrets of these cosmic enigmas. Now exploring another layer of this cosmic puzzle, we turn our attention to the possibility that supernova, the explosive deaths of massive stars, could be connected to fast radio bursts. These colossal events are among the most energetic phenomena in the universe, releasing an immense amount of energy in mere seconds. Could these stellar explosions be the source of FRBs? Supernova occur when a massive star exhausts its nuclear fuel and collapses under its own gravity, leading to a powerful explosion. This process not only scatters the star's material across space, but also creates extreme conditions that could potentially generate bursts of radio waves. Some scientists theorize that the shock waves and magnetic turbulence produced during a supernova might trigger the emission of FRBs. This idea is supported by the fact that supernova leave behind highly magnetized remnants like neutron stars or magnetars, which are already prime suspects in the FRB mystery. However, there's a catch. While supernova are incredibly energetic, they are also relatively rare events. FRB, on the other hand, are detected frequently, with new bursts being observed almost every day. This raises questions about whether supernova alone could account for the sheer number of FRBs we detect. To address this, researchers have proposed that perhaps only a specific type of supernova, one with unique characteristics, such as an exceptionally strong magnetic field or a rapid rotation rate, might be capable of producing FRBs. Another angle to consider is the timing. Supernova are one-time events, but some FRBs repeat. This inconsistency suggests that if supernova are involved, they might only be responsible for non-repeating FRBs. Alternatively, supernova could create the conditions necessary for FRBs to occur later, such as by leaving behind a magnetar that continues to produce bursts long after the initial explosion. Interestingly, there have been instances where FRBs have been detected in the vicinity of supernova remnants. For example, FRB 1911-20 was traced to a region near a young supernova remnant, hinting at a possible connection. While this doesn't prove causation, it does open the door to further investigation. As we piece together the clues, it's clear that supernova could play a role in the FRB mystery, but they are likely just one piece of the puzzle. The extreme environments they create might provide the necessary conditions for FRBs to occur, but other factors, such as the behavior of neutron stars or interactions with surrounding cosmic material, could also be at play. The search for answers continues, with astronomers using advanced telescopes and simulations to explore the potential link between supernova and FRBs. Each discovery brings us closer to understanding whether these cosmic explosions are indeed responsible for some, if not all, of these enigmatic bursts. And as we uncover more, the story of FRBs becomes not just a tale of mystery, but a testament to the dynamic and ever-changing nature of the universe. Now shifting our focus to another cosmic phenomenon, we dive into the potential connection between fast radio bursts and gamma-ray bursts. These two events are among the most powerful and mysterious occurrences in the universe, each releasing unimaginable amounts of energy in a fraction of a second. Could there be a link between them? Gamma-ray bursts are intense flashes of gamma rays, the highest energy form of light, often lasting just milliseconds to several minutes. They are thought to originate from catastrophic events like the collapse of massive stars or the merging of neutron stars. Similarly, fast radio bursts are brief but incredibly energetic radio signals that traverse vast cosmic distances. Both phenomena share a common trait. They are transient, appearing suddenly and disappearing just as quickly. Scientists have long wondered if these two events could be related. One theory suggests that gamma-ray bursts and FRBs might be different manifestations of the same underlying process. For instance, when a neutron star collapses or two neutron stars collide, the resulting explosion could produce both a gamma-ray burst and a fast radio burst. The gamma rays might be emitted directly from the explosion, while the radio waves could be generated as the explosion's shockwaves interact with surrounding material. There's also the possibility that gamma-ray bursts and FRBs could occur in sequence. A gamma-ray burst might be the initial, highly energetic event, while an FRB could follow as a secondary effect, produced by the remnants of the explosion or the resulting magneta. This idea gains some support from observations of gamma-ray bursts that are followed by radio emissions, though these are not identical to the fast radio bursts we detect. However, the connection remains unclear. While both gamma-ray bursts and FRBs are incredibly energetic, they are detected in different parts of the electromagnetic spectrum. Gamma-ray bursts are observed in high-energy gamma rays, while FRBs are detected in radio waves. This difference suggests that even if they share a common origin, the mechanisms producing them might be distinct. Adding to the complexity, gamma-ray bursts are often accompanied by visible light and X-rays, but FRBs typically do not have such counterparts. This raises questions about whether the two phenomena are truly linked or if their similarities are merely coincidental. To explore this further, astronomers have been searching for instances where both a gamma-ray burst and an FRB occur simultaneously or in close proximity. Such an observation would provide strong evidence of a connection. One intriguing case involves a gamma-ray burst detected in 2010, which was followed by a faint radio signal. While this signal was not a fast radio burst, it hinted at the possibility that gamma-ray bursts could produce radio emissions under certain conditions. More recently, in 2022, researchers detected a gamma-ray burst and a possible FRB originating from the same region of the sky. While this doesn't confirm a direct link, it certainly fuels the ongoing investigation. As we continue to explore the universe, the potential connection between gamma-ray bursts and fast radio bursts remains an exciting area of research. Whether they are two sides of the same cosmic coin or entirely separate phenomena, studying their relationship could shed light on the extreme physics at play in the universe. Each discovery brings us closer to understanding the true nature of these enigmatic events. Shifting our gaze to the heart of cosmic collisions, let's explore the theory that black hole mergers could be the source of fast radio bursts. These cataclysmic events, where two black holes spiral together and merge, are among the most energetic processes in the universe. Could they also be responsible for the enigmatic bursts of radio waves we detect? When two black holes merge, they release a tremendous amount of energy in the form of gravitational waves, ripples in the fabric of space-time. This energy is so immense that it momentarily outshines the entire universe. Some scientists propose that during such mergers, powerful electromagnetic emissions could also be produced, potentially including fast radio bursts. The idea is that the violent interaction of the black holes could create shock waves or magnetic fields capable of generating these brief but intense radio signals. One piece of evidence supporting this theory comes from the detection of gravitational waves by observatories like LIGO and Virgo. In several cases, black hole mergers have been observed, but no corresponding electromagnetic signals were detected. However, this doesn't necessarily rule out the possibility. The electromagnetic emissions from a merger might be too faint or too short-lived to be picked up by current telescopes, or they might be directed in a way that doesn't reach Earth. On the other hand, there are challenges to this idea. Black holes are known for their intense gravitational pull, which prevents even light from escaping. This raises the question of how radio waves could be emitted during a merger. One possibility is that the surrounding environment of the black holes plays a role. If the merging black holes are embedded in a dense cloud of gas and dust, the interaction between the merger and this material could produce the necessary conditions for an FRB. Alternatively, the merger could trigger phenomena like relativistic jets or magnetic reconnection, which might generate radio waves. Interestingly, some fast radio bursts have been traced back to regions of space where black holes are thought to reside. While this isn't definitive proof, it does add a layer of intrigue to the theory. Additionally, simulations of black hole mergers suggest that under certain conditions, electromagnetic signals could indeed be produced. These simulations show that the extreme physics involved in these events could create brief but powerful emissions, potentially aligning with the characteristics of FRBs. However, the evidence remains inconclusive. While the theoretical framework exists, no direct link between a black hole merger and a fast radio burst has been confirmed. Observations so far have not detected FRBs coinciding with confirmed black hole mergers, leaving this idea in the realm of possibility rather than certainty. As our understanding of black holes and fast radio bursts continues to evolve, the question of their potential connection remains open. Each new discovery brings us closer to unraveling the mysteries of these cosmic phenomena, and whether black hole mergers play a role in generating FRBs is a puzzle that scientists are eager to solve. The interplay between gravity, magnetism, and matter in these extreme environments could hold the key to understanding not just FRBs, but the most profound processes shaping our universe. Now turning to the tools that bring these cosmic whispers to our attention, let's explore how fast radio bursts are detected here on Earth. The key players in this cosmic detective work are radio telescopes, massive instruments designed to capture the faint radio signals traveling across the vastness of space. These telescopes act like giant ears, listening for the fleeting but powerful bursts that characterize FRBs. The process begins with the telescope's dish, which collects radio waves from the sky. Once captured, these signals are amplified and converted into data that scientists can analyze. But detecting an FRB is no simple task. These bursts last only milliseconds, making them incredibly difficult to catch in real time. To overcome this, telescopes often operate continuously, scanning the sky in all directions, hoping to catch a burst as it happens. Advanced software algorithms are then used to sift through the massive amounts of data, searching for the telltale patterns of an FRB. One of the most famous instruments in this search is the Parkes Observatory in Australia, which detected the very first FRB back in 2007. Since then, other telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have joined the hunt, identifying hundreds of bursts and significantly expanding our understanding of these phenomena. CHIME, in particular, has been groundbreaking due to its ability to scan large portions of the sky simultaneously, increasing the chances of capturing these elusive signals. However, detecting FRBs is only half the battle. Once a burst is found, scientists face the challenge of pinpointing its exact location in the sky. This is crucial for understanding where the burst originated and what might have caused it. To achieve this, multiple telescopes around the world often work together in a technique known as interferometry, combining their observations to create a more precise picture of the FRB source. Yet, even with these advanced tools, significant challenges remain. The sheer unpredictability of FRBs makes them hard to study. Unlike pulsars, which emit regular, rhythmic signals, FRBs appear randomly, leaving scientists with no way to predict when or where the next burst will occur. Additionally, the vast distances these signals travel mean they can be weakened or distorted by the time they reach Earth, making it difficult to extract clear information from the data. Another hurdle is the interference from human-made radio signals, which can obscure or mimic FRBs. Distinguishing between a genuine cosmic burst and terrestrial noise requires sophisticated filtering techniques and careful analysis. Despite these obstacles, the relentless efforts of scientists and the continuous improvement of technology are gradually unraveling the mysteries of fast radio bursts, bringing us closer to understanding these fleeting yet fascinating signals from the depths of space. Shifting our focus to the journey these signals undertake, we now delve into the role of the interstellar medium. As fast radio bursts travel across the cosmos, they don't move through empty space. Instead, they pass through the interstellar medium, a mix of gas, dust, and plasma that fills the vast regions between stars. This medium leaves a unique fingerprint on the FRB signals, offering scientists critical clues about the environments these bursts traverse. One of the most significant effects of the interstellar medium is dispersion. As an FRB travels, its radio waves interact with free electrons in the plasma of the interstellar medium. Higher frequency waves move slightly faster than lower frequency ones, causing the signal to spread out over time. This delay, known as the dispersion measure, helps scientists estimate how far the signal has traveled. The greater the dispersion, the more electrons the signal has encountered, indicating a longer journey through space. Another key effect is scattering. Tiny particles and irregularities in the interstellar medium can cause the radio waves to scatter, creating a smearing effect in the detected signal. This scattering can make the burst appear fainter and more diffuse, complicating the task of pinpointing its source or understanding its original structure. In some cases, the scattering is so severe that the burst becomes nearly unrecognizable by the time it reaches Earth. The interstellar medium can also cause Faraday rotation, a phenomenon where the polarization of the radio waves is twisted as they pass through magnetic fields. By studying this rotation, scientists can gain insights into the strength and direction of the magnetic fields the signal encountered along its path. This information is invaluable for mapping the magnetic landscape of our galaxy and beyond. Interestingly, the distortions caused by the interstellar medium aren't just obstacles, they're also tools. By analyzing these effects, researchers can learn about the composition and density of the material that lies between Earth and the source of the burst. This turns the interstellar medium into a cosmic lens, revealing details about the vast, unseen structures that shape our universe. Yet, these distortions also pose challenges. The smearing and weakening of signals make it harder to detect and study FRBs, especially those originating from the farthest reaches of space. To overcome this, scientists use advanced techniques to correct for these distortions, reconstructing the original signal as accurately as possible. This meticulous process is essential for uncovering the true nature of these enigmatic bursts. As we continue to explore the mysteries of fast radio bursts, the interstellar medium emerges as both a hurdle and a guide. Its influence on these signals not only shapes what we observe, but also provides a window into the hidden fabric of the cosmos, offering a deeper understanding of the universe's intricate workings. Stepping into the next chapter of our exploration, we turn our attention to one of the most intriguing fast radio bursts ever detected, FRB 180,916. Unlike other FRBs, this one stands out not just for its signal, but for its extraordinary regularity. It follows a peculiar 16-day cycle, with bursts occurring in a predictable pattern that has left scientists both fascinated and puzzled. What could possibly cause such a precise rhythm in an otherwise chaotic cosmic phenomenon? The first clue lies in the nature of the cycle itself. FRB 180,916 emits bursts for about 4 days, followed by a 12-day period of silence, repeating this pattern like clockwork. This regularity suggests that the source is influenced by a specific mechanism or structure in its environment. One leading theory points to the possibility of an orbiting companion, such as a star or a black hole, that modulates the FRB's activity. As the companion moves in its orbit, it could periodically block or amplify the bursts, creating the observed pattern. Another compelling idea revolves around the source being a highly magnetized neutron star or magnetar. Magnetars are known for their intense magnetic fields and erratic bursts of energy. If FRB 180,916 originates from a magnetar, the 16-day cycle could be tied to the star's rotation or precession, a wobbling motion in its axis. This movement could align the beam of radio waves with Earth only during specific intervals, producing the observed cyclical bursts. Alternatively, some researchers speculate that the cycle could be linked to the environment surrounding the FRB source. For instance, if the source resides in a binary system with a massive star, stellar winds or debris from the companion could periodically obscure or alter the FRB signal. This interaction could create the distinctive on and off pattern we detect. The mystery deepens when considering the sheer precision of the cycle. Even with these theories, scientists are still grappling with the question of how such a regular pattern can be maintained over time. Is it the result of a perfectly tuned cosmic dance, or are there other unknown forces at play? FRB 180,916 challenges our understanding of FRBs, pushing us to rethink what we know about these enigmatic signals. As we continue to study this remarkable phenomenon, FRB 180,916 offers a unique opportunity to unravel the secrets of fast radio bursts. Its regularity provides a rare window into the mechanisms that govern these cosmic explosions, bringing us one step closer to solving one of the universe's most captivating mysteries. With every burst, it reminds us that the cosmos is filled with wonders waiting to be understood, and that even the strangest patterns can lead us to profound discoveries. Shifting our gaze to another fascinating possibility, let's explore whether neutron star collisions could be responsible for some fast radio bursts. These cataclysmic events, where two neutron stars spiral into each other and merge, are among the most energetic phenomena in the universe. When such a collision occurs, it releases an immense amount of energy, often accompanied by gravitational waves and bursts of light across the electromagnetic spectrum. Could these violent encounters also produce the mysterious signals we call FRBs? One key piece of evidence supporting this theory lies in the 2017 detection of a neutron star collision, which produced not only gravitational waves but also a gamma-ray burst and a kilonova, an explosion that creates heavy elements like gold and platinum. While no FRB was detected in this specific event, it highlighted the potential for neutron star mergers to emit powerful, short-lived bursts of energy. This raises the tantalizing question: could some FRBs originate from similar collisions that simply haven't been observed yet? Advocates of this theory argue that neutron star collisions have the right ingredients to produce FRBs. The intense magnetic fields and rapid motion of the merging stars could generate the conditions necessary for these radio bursts. Additionally, the material ejected during the collision could interact with surrounding plasma, creating the kind of complex environment that might shape an FRB signal. However, skeptics point out that neutron star mergers are relatively rare events, and if they were the primary source of FRBs, we would expect to detect far fewer of these bursts than we currently observe. Comparing this theory to others, neutron star collisions offer a compelling, albeit not definitive, explanation. Unlike magnetars, which might produce repeating FRBs, or black hole mergers, which are still speculative as FRB sources, neutron star collisions provide a clear mechanism for generating one-off bursts. Yet, the rarity of these events compared to the frequency of FRB detections suggests that they might account for only a fraction of the observed signals. As researchers continue to study both neutron star collisions and FRBs, the connection between the two remains an open question. Each hypothesis brings us closer to understanding these cosmic mysteries, but the true answer may lie in a combination of sources. Neutron star collisions, with their immense energy and dramatic aftermath, are a promising piece of the puzzle, reminding us that the universe is full of extraordinary events waiting to be explored. Now shifting our focus to one of the most enigmatic substances in the cosmos, let's consider whether dark matter could play a role in the creation of fast radio bursts. Dark matter, which makes up about 27% of the universe, is invisible and interacts only through gravity, yet its presence is felt in the way galaxies rotate and cluster together. Could this mysterious substance contribute to the bursts of radio waves that leave scientists puzzled? One intriguing possibility is that dark matter particles, when interacting or decaying, could release energy in the form of radio waves. Some theories suggest that dense regions of dark matter, such as halos around galaxies, might create conditions where these interactions occur, potentially generating FRBs. Additionally, if dark matter forms exotic objects like dark stars or primordial black holes, these could be candidates for FRB sources. The idea is speculative but opens up a fascinating avenue for exploration. Another angle considers the interaction between dark matter and ordinary matter. If dark matter particles collide with neutron stars or other dense astrophysical objects, the resulting energy release might produce FRBs. This scenario would tie together two cosmic mysteries, dark matter and FRBs, but it remains highly theoretical. So far, no direct evidence links dark matter to FRBs, and the lack of detectable dark matter interactions makes this hypothesis challenging to test. Critics of this theory argue that the properties of dark matter, as currently understood, don't align neatly with the observed characteristics of FRBs. For instance, FRBs are highly energetic and localized events, while dark matter is diffuse and widespread. Moreover, the unpredictable and sporadic nature of FRBs doesn't easily fit with the steady, gravitational influence of dark matter. Despite these challenges, the idea remains a compelling area of research, especially as scientists continue to search for ways to detect and understand dark matter. As we ponder this possibility, it's worth noting that dark matter's role in FRBs, if any, would likely be indirect. Perhaps it creates the conditions or environments necessary for FRBs to occur, rather than directly producing the bursts themselves. While this theory is still in its infancy, it highlights the interconnectedness of cosmic mysteries and reminds us that the universe often defies our expectations. Exploring the connection between dark matter and FRBs pushes the boundaries of our understanding, blending the known with the unknown. As scientists continue to study both phenomena, the answers they uncover may not only solve the puzzle of FRBs but also shed light on the nature of dark matter itself. This dual mystery underscores the endless surprises waiting to be discovered in the cosmos. Now turning to the remnants of once bright stars, let's consider whether white dwarfs could be responsible for fast radio bursts. White dwarfs are the dense cores left behind after stars like our Sun exhaust their nuclear fuel and shed their outer layers. These stellar remnants are incredibly compact, packing a mass similar to the Sun into a volume about the size of Earth. But could these aging stars produce the sudden, intense bursts of radio waves we detect as FRBs? One possibility involves the violent interactions between white dwarfs and other cosmic objects. For example, if a white dwarf is part of a binary system orbiting another star, it could pull material from its companion. Over time, this accumulated material might trigger an explosion known as a nova or even a more powerful thermonuclear event. Such outbursts could potentially release energy in the form of radio waves, creating an FRB. Additionally, white dwarfs colliding with each other or with neutron stars could produce immense energy, possibly leading to an FRB. Another scenario focuses on the magnetic fields of white dwarfs. Some white dwarfs, known as highly magnetized white dwarfs or magnetized dwarfs, possess magnetic fields trillions of times stronger than Earth. These fields could accelerate particles, generating intense bursts of radiation, including radio waves. If this process occurs rapidly and with enough energy, it might produce the brief, bright signals we observe as FRBs. However, there are challenges to this theory. Most white dwarfs are relatively stable and quiet, unlike the dynamic and often unpredictable sources of FRBs. Additionally, the energy required to produce an FRB seems to exceed what a typical white dwarf could generate. While some extreme white dwarf events might come close, the connection remains speculative. Despite these hurdles, the idea of white dwarfs as FRB sources is intriguing because it ties together two distinct astronomical phenomena. White dwarfs represent the final stage of stellar evolution for most stars, while FRBs are among the most mysterious signals in the universe. Exploring this potential link could deepen our understanding of both white dwarfs and the origins of FRBs. As we consider this possibility, it's worth noting that white dwarfs might not directly produce FRBs but could instead create the conditions necessary for them. For example, a white dwarf's magnetic field or its interactions with other objects might trigger processes that lead to an FRB. This indirect role would still make white dwarfs a fascinating piece of the FRB puzzle. Whether white dwarfs are directly or indirectly involved in FRBs, the exploration of this connection highlights the complexity of the cosmos. Each piece of the puzzle, from the remnants of dead stars to the bursts of radio waves traversing the universe, reminds us of the endless mysteries waiting to be unraveled. Now venturing into the realm of theoretical physics, let's examine the intriguing possibility that cosmic strings could be the source of fast radio bursts. Cosmic strings are hypothetical one-dimensional defects in space-time, thought to have formed during the early universe as a result of phase transitions in the fabric of reality. These cosmic anomalies are incredibly thin but can stretch across vast distances, carrying immense energy. But how could such objects produce the sudden, intense bursts of radio waves we detect as FRBs? One theory suggests that cosmic strings might vibrate or snap under their own tension, releasing bursts of energy in the process. These vibrations could generate gravitational waves and electromagnetic radiation, including radio waves. If the energy release is sudden and concentrated, it might produce signals similar to FRBs. Additionally, interactions between cosmic strings and other cosmic structures, such as black holes or neutron stars, could create shock waves or bursts of energy that manifest as FRBs. Another scenario involves the immense gravitational fields associated with cosmic strings. As these objects warp space-time, they could accelerate particles or induce extreme magnetic fields in their vicinity. These processes might then generate bursts of radio waves detectable from Earth. The sheer scale and energy of cosmic strings make them a compelling, though highly speculative, candidate for FRB origins. However, the idea of cosmic strings as FRB sources faces significant challenges. cosmic strings remain purely theoretical with no direct evidence of their existence. Their detection would require groundbreaking advancements in observational technology. Furthermore, even if cosmic strings exist, the mechanisms by which they might produce FRBs are still poorly understood and remain in the realm of conjecture. Despite these uncertainties, exploring the potential connection between cosmic strings and FRBs opens up fascinating possibilities. If confirmed, it would not only solve the mystery of FRB origins, but also provide evidence for cosmic strings, offering profound insights into the early universe and the nature of space-time itself. As we delve into this speculative theory, it's important to remember that cosmic strings represent one of many possible explanations for FRBs. While the idea is tantalizing, it underscores the boundless creativity and curiosity driving scientific inquiry. Whether cosmic strings are behind FRBs or not, the pursuit of such theories reminds us of the vast, uncharted territories waiting to be explored in the cosmos. Now shifting our gaze beyond conventional astrophysics, let's consider one of the most provocative theories surrounding fast radio bursts, the possibility that they could be signals from extraterrestrial civilizations. This idea, while highly speculative, has captured the imagination of both scientists and the public alike. Could these mysterious bursts of radio waves be deliberate messages from intelligent beings in the cosmos? The concept is rooted in the idea that advanced civilizations might use powerful radio signals to communicate across vast interstellar distances. The characteristics of FRBs, brief, intense, and seemingly originating from faraway galaxies, make them a candidate for such artificial transmissions. Supporters of this theory point to the repeating nature of some FRBs as potential evidence, suggesting that deliberate communication would require repeated signals rather than one-off bursts. However, the likelihood of this explanation faces significant skepticism. The immense energy required to produce FRBs would demand technology far beyond anything humanity currently possesses. For a civilization to generate such signals, they would need to harness energy on a scale comparable to entire stars, raising questions about their feasibility. Additionally, the natural explanations for FRBs, such as neutron stars or magnetars, are already well supported by scientific evidence, making the alien hypothesis less necessary from a theoretical standpoint. Another challenge is the lack of any discernible pattern or information in FRB signals. If these bursts were intentional messages, we might expect them to contain some form of encoded data or structure. Yet, so far, FRBs appear random and unstructured, aligning more closely with natural astrophysical phenomena than artificial communication. Despite these hurdles, the idea of FRBs as extraterrestrial signals remains an intriguing possibility. It highlights humanity's enduring fascination with the question of whether we are alone in the universe. Even if the theory is unlikely, the pursuit of such ideas encourages us to think creatively and explore the boundaries of what might be possible. As we weigh the merits of this hypothesis, it's essential to approach it with both curiosity and critical thinking. While the notion of alien civilizations behind FRBs is captivating, it remains one of many potential explanations in the ongoing quest to unravel these cosmic mysteries. Whether FRBs are natural or artificial, their discovery continues to inspire us to look deeper into the cosmos and ponder the profound questions it holds. Now stepping into the realm of the extremely small, let's explore how quantum physics might influence the generation of fast radio bursts. Could the bizarre and often counterintuitive behavior of particles at the quantum level be responsible for these cosmic signals? This idea takes us beyond the classical explanations of neutron stars and magnetars, venturing into a world where the rules of physics as we know them start to break down. One intriguing possibility is that quantum effects such as quantum tunneling or entanglement could play a role in the creation of FRBs. Quantum tunneling, for instance, allows particles to pass through barriers that would be insurmountable under classical physics. If such phenomena occur in extreme astrophysical environments, like the intense magnetic fields around neutron stars, they might trigger the sudden release of energy we observe as FRBs. Similarly, quantum entanglement, where particles remain connected across vast distances, could provide a mechanism for the synchronization of energy bursts across cosmic scales. Another area of interest is the potential role of quantum vacuum fluctuations. In the quantum realm, even empty space is alive with energy, as particles and antiparticles pop in and out of existence. In highly energetic environments, these fluctuations could amplify and release bursts of energy detectable as FRBs. While this remains speculative, it opens up a fascinating avenue for exploring how quantum processes might influence events on a cosmic scale. Critics, however, caution that quantum effects are typically observed at microscopic scales and may not translate easily to the enormous energies and distances involved in FRBs. The mechanisms proposed would need to be scaled up dramatically to account for the immense power of these bursts, raising questions about their feasibility. Additionally, current models of neutron stars and magnetars already provide robust explanations for FRBs, making quantum-based theories less necessary but no less intriguing. Despite these challenges, the exploration of quantum physics in the context of FRBs underscores the interconnectedness of the universe, from the smallest particles to the largest cosmic events. It reminds us that the answers to some of the universe's greatest mysteries may lie at the intersection of different fields of science. As we delve deeper into the quantum frontier, it's clear that FRBs continue to challenge our understanding of the cosmos. Whether quantum physics plays a direct role in their generation or not, the pursuit of such theories pushes the boundaries of our knowledge, inviting us to consider new and unconventional possibilities. And in doing so, we may find answers not just to the mystery of FRBs, but to the broader questions about the nature of the universe itself. Now shifting our focus to another cosmic phenomenon, let's examine the potential connection between fast radio bursts and gravitational waves. Both are among the most energetic events in the universe, but could they be linked? Gravitational waves, ripples in space-time caused by massive collisions like those between black holes or neutron stars, were first detected in 2015, opening a new window into the cosmos. Similarly, FRBs are intense bursts of radio waves that last mere milliseconds, yet their origins remain shrouded in mystery. Could these two phenomena share a common source or mechanism? One compelling theory suggests that the same cataclysmic events that produce gravitational waves might also generate FRBs. For instance, when two neutron stars collide, they can send out both gravitational waves and electromagnetic radiation, including radio bursts. This idea gained traction after the historic detection of gravitational waves from a neutron star merger in 2017. During this event, astronomers also observed a short gamma-ray burst, a close cousin of FRBs, raising the possibility that such collisions could produce both gravitational waves and radio bursts. Another scenario involves black hole mergers. While these events are known to produce gravitational waves, they are typically thought to emit little to no electromagnetic radiation. However, some researchers speculate that under certain conditions, such as the presence of a surrounding accretion disk or magnetic fields, black hole mergers could also trigger FRBs. This would provide a direct link between the two phenomena, offering clues about the environments and processes involved. There's also the question of timing. Gravitational waves and FRBs are both transient events occurring suddenly and unpredictably. If they are connected, detecting them simultaneously could provide unprecedented insights into their origins. However, this requires precise coordination between gravitational wave detectors like LIGO and Virgo and radio telescopes capable of pinpointing FRBs. While such detections have yet to be confirmed, the possibility remains an exciting area of research. Critics, however, point out that while the connection is intriguing, the evidence remains circumstantial. Gravitational waves and FRBs have not yet been definitively linked to the same events, and the mechanisms proposed are still speculative. Additionally, the vast majority of FRBs do not seem to coincide with gravitational wave detections, suggesting that if a connection exists, it may only apply to a subset of these bursts. Despite the uncertainties, exploring the potential link between gravitational waves and FRBs highlights the interconnected nature of cosmic phenomena. It reminds us that the universe is a dynamic and complex system where different types of signals can emerge from the same underlying processes. Whether or not gravitational waves are directly tied to FRBs, investigating this possibility pushes the boundaries of our understanding and brings us closer to unraveling the mysteries of the cosmos. Shifting our gaze to the subtle yet pervasive presence of cosmic dust, we delve into its potential influence on fast radio bursts. Cosmic dust, composed of tiny particles scattered throughout galaxies, plays a significant role in shaping our observations of the universe. But how does it impact the detection of FRBs? The answer lies in the interaction between these bursts and the dusty environments they traverse. As FRBs travel through space, they encounter cosmic dust which can absorb or scatter their radio waves. This process, known as extinction, can weaken the signal by the time it reaches Earth. In some cases, the dust might completely obscure the FRB, making it undetectable by our radio telescopes. This raises the question, could some of the FRBs we've missed be hidden behind dense clouds of cosmic dust? Moreover, the properties of the dust itself can affect the FRB signals. For instance, dust grains aligned by magnetic fields can polarize the radio waves, altering their characteristics. Studying these changes can provide valuable clues about the environments where FRBs originate. By analyzing how dust affects the polarization of FRBs, scientists can infer details about the magnetic fields and dust composition in distant galaxies. However, not all effects of cosmic dust are obstructive. In some cases, the presence of dust can actually help us detect FRBs more precisely. When an FRB passes through a dusty region, the dust can act as a lens, bending and focusing the radio waves. This phenomenon, known as gravitational lensing, can amplify the signal, making it easier to detect and study. Such events offer a unique opportunity to examine both the FRBs and the properties of the dust clouds they encounter. Despite these insights, cosmic dust remains a complex and often unpredictable factor in FRB research. Its distribution varies widely across the universe, and its effects on FRB signals can differ depending on the dust's composition, density, and alignment. As a result, scientists continue to investigate how cosmic dust shapes our observations of these mysterious bursts, seeking to unravel its role in the larger puzzle of FRBs. This exploration of cosmic dust reminds us that the universe is filled with subtle, often overlooked elements that can significantly impact our understanding of cosmic phenomena. By studying how dust interacts with FRBs, we not only gain insight into these bursts but also uncover the intricate dynamics of the environments they traverse. Next, we turn to another fascinating aspect of FRBs, their polarization and what it reveals about their origins and journeys through space. Now turning our attention to the invisible forces that mold the cosmos, let's explore the role of magnetic fields in shaping fast radio bursts. Magnetic fields are powerful yet often unseen, elements that permeate the universe, influencing everything from the birth of stars to the behavior of galaxies. But how do they impact FRBs? The answer lies in the way these fields interact with the bursts as they travel through space. Magnetic fields can alter the polarization of FRBs, a key property that reveals the orientation of the radio waves. When an FRB passes through regions with strong magnetic fields, the fields can twist and align the radio waves, a process known as Faraday rotation. By studying the degree and direction of this rotation, scientists can infer the strength and structure of the magnetic fields along the FRB's path. This information provides a unique window into the environments where these bursts originate and traverse. Additionally, magnetic fields may play a role in generating FRBs themselves. One leading theory suggests that highly magnetized neutron stars, known as magnetars, could be the source of some FRBs. The immense magnetic energy stored in these stars could be released in sudden, explosive events, producing the intense bursts we observe. This connection between magnetic fields and FRBs offers a compelling explanation for their immense energy and fleeting nature. However, magnetic fields don't just shape FRBs at their source. As the bursts travel through space, they encounter magnetic fields in interstellar and intergalactic spaces, which can further modify their properties. These interactions can scatter the radio waves, broaden their frequency range, or even split them into multiple components. By analyzing these changes, scientists can map the distribution and strength of magnetic fields across vast cosmic distances. Despite these insights, the precise role of magnetic fields in FRBs remains an area of active research. Their effects can vary widely depending on the strength, orientation, and environment of the fields, making them a complex and dynamic factor in the study of these cosmic signals. As astronomers continue to unravel the mysteries of FRBs, magnetic fields stand out as a crucial piece of the puzzle, offering clues about the origins and journeys of these enigmatic bursts. This exploration of magnetic fields underscores their profound influence on the universe, reminding us that even the most subtle forces can shape the phenomena we observe. With this understanding in place, we now move to another intriguing aspect of FRBs, the role of neutrino emissions and whether these elusive particles might be linked to these cosmic bursts. As we venture further into the depths of cosmic mysteries, let's consider the potential connection between fast radio bursts and one of the universe's most elusive particles, neutrinos. Neutrinos are nearly massless particles that travel through space at incredible speeds, rarely interacting with matter. Their ghostly nature makes them difficult to detect, but their presence could hold important clues about the origins of FRBs. Could these mysterious bursts be accompanied by neutrino emissions? The idea that neutrinos might be linked to FRBs stems from the extreme environments where these bursts are thought to occur. Neutrinos are often produced in high-energy events such as supernova, neutron star collisions, or the collapse of massive stars. If FRBs originate from similarly energetic processes, it's possible that neutrinos could be generated alongside the radio burst. For example, if a magnetar experiences a catastrophic flare or a neutron star collides with another dense object, such an event could release both neutrinos and the intense radio waves we detect as FRBs. However, detecting neutrinos associated with FRBs is a significant challenge. Neutrinos rarely interact with detectors, and their signals can easily be overshadowed by other cosmic events. Despite this, scientists have begun searching for possible correlations between neutrino detections and the timing of FRBs. Observatories like the Ice Cube Neutrino Observatory in Antarctica are constantly monitoring the skies for neutrino signals, hoping to catch a glimpse of these particles coinciding with FRB events. So far, no definitive link has been established, but the search continues, driven by the tantalizing possibility of uncovering a deeper connection. If neutrinos are indeed produced alongside FRBs, it would provide valuable insights into the mechanisms behind these bursts. Neutrinos could reveal details about the energy release, particle acceleration, and even the types of objects involved in generating FRBs. This would not only enhance our understanding of FRBs, but also shed light on the broader processes shaping the universe's most extreme environments. As we ponder this intriguing possibility, it's clear that the search for neutrino emissions linked to FRBs is still in its early stages. Yet, the potential discovery of such a connection would be a monumental step forward, bridging the gap between radio astronomy and particle physics. With that in mind, let's shift our focus to another cosmic phenomenon that might hold clues to the mysteries of FRBs: the role of exotic matter and whether it could be involved in the generation of these enigmatic signals. Now, as we delve into the realm of cosmic possibilities, let's explore the intriguing role of exotic matter in the generation of fast radio bursts. Exotic matter refers to hypothetical forms of matter that differ significantly from the particles and substances we encounter in our everyday world. Among these, quark stars stand out as a particularly fascinating candidate. Quark stars are theorized to be even denser than neutron stars, composed almost entirely of quarks, the fundamental building blocks of matter. If these stars exist, they could hold the key to understanding some of the universe's most energetic phenomena, including FRBs. The concept of quark stars arises from the idea that, under extreme pressure and density, the neutrons in a neutron star might break down into their constituent quarks, forming a new state of matter. This process could release an enormous amount of energy, possibly manifesting as FRBs. The extreme conditions within a quark star, such as its immense gravitational pull and intense magnetic fields, could also create the perfect environment for generating these mysterious radio bursts. If quark stars are indeed the source of some FRBs, it would revolutionize our understanding of stellar evolution and the nature of matter itself. Another aspect of exotic matter that could be linked to FRBs is strange matter, a hypothetical form of matter composed of strange quarks. Strange matter is thought to be incredibly stable and could exist in the cores of certain dense stellar objects. If FRBs originate from such objects, the interaction between strange matter and its surroundings might produce the intense energy bursts observed. While this idea remains speculative, it opens up exciting avenues for exploring the connections between exotic matter and cosmic phenomena. Detecting exotic matter directly is a monumental challenge, as it would require observing the internal structure of objects billions of light years away. However, indirect evidence could come from studying the properties of FRBs themselves. For example, if FRBs exhibit unique patterns or energy signatures that cannot be explained by neutron stars or black holes alone, it could suggest the presence of exotic matter. Advances in radio astronomy and theoretical physics are bringing us closer to testing these ideas, offering hope for uncovering the true nature of FRBs. The exploration of exotic matter in the context of FRBs not only deepens our understanding of these enigmatic signals, but also pushes the boundaries of our knowledge of the universe. Whether quark stars, strange matter, or other exotic forms are involved, the pursuit of these ideas challenges us to think beyond conventional astrophysics and imagine the extraordinary. As we continue to unravel the mysteries of FRBs, the role of exotic matter remains a captivating frontier, inviting us to question what lies beyond the known limits of the cosmos. With this in mind, let's turn our attention to another cosmic puzzle: the influence of time dilation on our observations of these fleeting bursts. Now shifting our perspective to the fabric of space and time, let's explore how time dilation might influence our observations of fast radio bursts. Time dilation, a phenomenon predicted by Einstein's theory of relativity, occurs when time passes at different rates depending on the strength of a gravitational field or the speed of an object. Near massive objects like black holes or neutron stars, where gravity is incredibly intense, time slows down significantly compared to regions with weaker gravitational fields. This effect could have profound implications for how we perceive FRBs originating from such extreme environments. Imagine an FRB emitted close to a massive object like a black hole. Due to time dilation, the burst might take longer to escape the intense gravitational pull, causing it to appear slower or stretched out when observed from Earth. Conversely, if the source of an FRB is moving at high speeds relative to us, relativistic effects could compress the observed signal, making it appear shorter or more intense. These distortions could complicate our efforts to pinpoint the exact location and nature of FRB sources, adding another layer of mystery to their study. Time dilation also raises questions about the timing of FRB detections. If an FRB originates near a massive object, the delay caused by gravitational time dilation could make it difficult to determine the burst's true arrival time. This effect might explain why some FRBs seem to arrive unexpectedly, or why their signals appear altered in ways that current models cannot fully account for. Understanding these distortions could be key to refining our detection methods and improving the accuracy of FRB observations. Moreover, time dilation could play a role in the apparent randomness of FRB detections. If FRBs are emitted from objects orbiting massive bodies, the gravitational effects could cause their signals to arrive at irregular intervals, making them appear sporadic and unpredictable. This variability might explain why some FRBs are detected only once, while others repeat at seemingly random times. By accounting for time dilation, scientists could potentially uncover patterns or cycles in FRB activity that are currently hidden. The study of time dilation's impact on FRBs not only deepens our understanding of these cosmic signals, but also highlights the interconnectedness of space, time, and gravity. As we continue to explore the universe's most extreme environments, the interplay between time dilation and FRBs offers a fascinating glimpse into the complexities of relativistic physics. With this in mind, let's turn our attention to another intriguing factor: the role of cosmic expansion in shaping the properties of these enigmatic bursts. Now diving into the broader canvas of the cosmos, let's consider how the expansion of the universe itself might shape the behavior of fast radio bursts. As you may know, the universe is not static, it's constantly growing, with galaxies moving away from one another due to the force of dark energy. This expansion stretches the fabric of space and time, and it could have significant effects on how we detect and interpret FRBs. One of the most direct impacts of cosmic expansion is the phenomenon known as redshift. As FRBs travel across vast distances, the expansion of the universe stretches their wavelengths, shifting them toward the red end of the electromagnetic spectrum. This redshift can provide crucial clues about the distance to an FRB source and the conditions of the universe at the time the burst was emitted. By analyzing the degree of redshift, scientists can estimate how far the signal has traveled and how long it's been journeying through space. Cosmic expansion also influences the energy we observe from FRBs. As space stretches, the energy of the burst is diluted over larger distances, meaning that more distant FRBs may appear fainter than they actually are at the source. This effect could explain why some FRBs seem to vary in brightness, even if their original energy output was similar. Additionally, the expansion of the universe might cause some FRBs to be missed entirely, as their signals could become too faint to detect by the time they reach Earth. The rate of cosmic expansion also plays a role in the timing of FRB detections. As the universe expands, the time it takes for light or radio signals to travel between 2 points increases. This means that FRBs emitted billions of years ago might only now be reaching us, offering a glimpse into the universe's distant past. Understanding this time delay could help scientists build a more accurate timeline of cosmic events and better understand the evolution of FRB sources over time. Finally, the expansion of the universe adds another layer of complexity to the mystery of FRBs. It raises questions about whether the properties we observe today, such as their frequency, brightness, and distribution, are truly representative of their original state, or if they've been subtly altered by the stretching of space. By accounting for cosmic expansion, researchers can refine their models of FRB behavior and gain deeper insights into these enigmatic signals. As we unravel the role of cosmic expansion in shaping FRBs, we're not just studying the bursts themselves, we're exploring the very fabric of the universe. This connection between FRBs and the cosmos highlights how these mysterious signals can serve as probes into the large-scale structure and evolution of space itself. With this in mind, let's shift our focus to another fascinating aspect, the potential link between FRBs and cosmic rays. Now turning to another intriguing possibility, let's explore the potential link between fast radio bursts and cosmic rays. Cosmic rays are highly energetic particles that travel through space at nearly the speed of light, often originating from violent cosmic events like supernova or active galactic nuclei. These particles interact with magnetic fields and matter as they journey through the universe, and some scientists have wondered if they might be connected to the mysterious signals we know as FRBs. One theory suggests that cosmic rays could play a role in triggering FRBs. For instance, when cosmic rays collide with dense regions of plasma or magnetic fields around neutron stars or black holes, they might generate the intense bursts of radio energy we detect as FRBs. This idea raises the possibility that FRBs and cosmic rays could be two sides of the same cosmic coin, both born from the same extreme astrophysical environment. However, the exact mechanisms behind such interactions remain unclear, leaving this theory open for further investigation. Another angle considers whether FRBs themselves could be a source of cosmic rays. If FRBs are produced by highly energetic processes such as neutron star mergers or magnetoflares, they might also accelerate particles to cosmic ray energies. This would mean that FRBs and cosmic rays could be part of a broader family of high-energy phenomena, all stemming from the most violent events in the universe. While this connection is speculative, it highlights the potential for FRBs to shed light on the origins of cosmic rays. It's also worth noting that both cosmic rays and FRBs are influenced by the same cosmic landscapes. As these particles and signals travel through space, they interact with magnetic fields, plasma, and other interstellar or intergalactic matter. Studying how these interactions affect cosmic rays and FRBs could provide valuable insights into the environments they traverse and the processes that shape their behavior. Despite these intriguing possibilities, the relationship between cosmic rays and FRBs remains a mystery. Current observations haven't yet provided definitive evidence linking the two, but this doesn't rule out the possibility. Future advancements in technology, such as more sensitive detectors and multi-messenger astronomy, could help uncover whether these cosmic phenomena are truly connected. As we continue to unravel the mysteries of FRBs, the potential connection to cosmic rays serves as a reminder of the interconnected nature of the universe. Whether or not they are directly related, both phenomena offer unique windows into the high-energy processes that shape our cosmos. With this in mind, let's move forward to another fascinating aspect, the role of dark energy in the generation or propagation of FRBs. Shifting our gaze to one of the most mysterious forces in the universe, we now consider the role of dark energy in the context of fast radio bursts. Dark energy, the enigmatic force driving the accelerated expansion of the universe, has puzzled scientists for decades. Could it also have a hand in shaping or influencing FRBs? While the idea may seem far-fetched, it's worth exploring the potential connections between these two cosmic mysteries. One possibility is that dark energy could affect the propagation of FRBs as they travel through space. As the universe expands, dark energy stretches the fabric of space-time, potentially altering the paths and properties of radio signals. This could explain why some FRBs appear distorted or delayed when they reach Earth. By studying these effects, scientists might gain new insights into both FRBs and the nature of dark energy itself. Another angle suggests that dark energy could influence the environments where FRBs originate. For instance, if FRBs are produced in regions of intense gravitational activity, such as near black holes or neutron stars, dark energy's effects on space-time could play a role in triggering these bursts. The interplay between dark energy and extreme astrophysical objects remains a fascinating area of speculation, though concrete evidence is still elusive. It's also worth considering whether dark energy could be indirectly linked to FRBs through its impact on cosmic evolution. As the universe expands, dark energy shapes the distribution of galaxies, stars, and other cosmic structures. These changes could influence the conditions under which FRBs are generated, making dark energy a silent orchestrator of these high-energy events. While these ideas are speculative, they highlight the interconnectedness of cosmic phenomena. Whether or not dark energy directly influences FRBs, exploring this potential connection opens new avenues for understanding both mysteries. As we continue to probe the depths of the universe, the interplay between dark energy and FRBs may yet reveal surprising insights into the forces that shape our cosmos. With this in mind, we now turn our attention to another intriguing aspect of FRBs, the role of neutron star quakes and how they might contribute to these enigmatic bursts. Now turning to the fascinating phenomenon of neutron star quakes, we delve into another potential source of fast radio bursts. Neutron stars, the dense remnants of massive stars, are known for their extreme gravitational and magnetic fields. These conditions can lead to powerful quakes, massive shifts in the star's crust that release immense amounts of energy. Could these quakes be the key to understanding some FRBs? One compelling theory suggests that when a neutron star experiences a quake, it can generate intense bursts of electromagnetic radiation. This energy could manifest as an FRB, shooting out into space in a fraction of a second. The sheer force of these quakes, combined with the neutron star's magnetic field, might be enough to produce the incredibly bright radio signals we detect. Supporting this idea, scientists have observed that neutron stars often undergo dramatic changes in their rotation after a quake, known as glitches. These glitches suggest that significant energy is being released, which could align with the energy scales of FRBs. Additionally, some repeating FRBs show patterns that could be linked to the periodic activity of a neutron star, such as quakes or other internal processes. However, not all neutron star quakes necessarily produce FRBs. The conditions would need to be just right: specific alignments of magnetic fields, crust composition, and energy release. This makes the theory both intriguing and challenging to prove. Exploring the connection between neutron star quakes and FRBs not only sheds light on these mysterious bursts, but also deepens our understanding of neutron stars themselves. By studying the mechanics of these quakes, scientists can uncover new details about the extreme environments in which they occur. As we continue to investigate, the role of neutron star quakes in producing FRBs remains a tantalizing possibility, offering yet another piece of the puzzle in our quest to understand these cosmic enigmas. Moving forward, we'll examine another fascinating aspect of FRBs, the role of accretion disks and how they might contribute to these bursts. As we venture further into the mysteries of fast radio bursts, let's turn our attention to the swirling maelstroms of energy known as accretion disks. These disks, composed of gas and dust, orbit around black holes and neutron stars, feeding them material and releasing enormous amounts of energy in the process. Could these cosmic powerhouses be responsible for generating some FRBs? One intriguing possibility is that the extreme conditions within an accretion disk could create the perfect environment for FRBs. As matter spirals inward, it heats up to incredible temperatures, producing intense electromagnetic radiation. In some cases, this energy might be channeled into powerful, focused bursts that escape into space as FRBs. The chaotic nature of these disks, with their turbulent magnetic fields and violent interactions, could easily give rise to such sudden and intense emissions. Another theory suggests that the interaction between a neutron star's magnetic field and its surrounding accretion disk could trigger FRBs. When the star's magnetic field lines become twisted and snap, they could release a burst of energy that travels through the disk and out into the cosmos. This process, known as magnetic reconnection, is a leading candidate for explaining the immense power behind these bursts. However, not all accretion disks are the same. The size, density, and magnetic properties of a disk could determine whether it's capable of producing an FRB. For instance, disks around supermassive black holes might behave differently than those around smaller neutron stars, leading to varying outcomes. This complexity makes it challenging to pinpoint exactly how or when these disks might generate FRBs. Studying the role of accretion disks in FRB production not only helps us understand these bursts, but also provides deeper insights into the behavior of black holes and neutron stars. By observing how matter behaves in these extreme environments, scientists can uncover new details about the forces at play in the universe. As we continue to explore this connection, the role of accretion disks remains a captivating area of research, offering yet another layer of intrigue in the ongoing quest to unravel the mysteries of fast radio bursts. Next, we'll investigate another compelling theory: the role of magnetic reconnection in producing these enigmatic signals. Now turning to the fascinating process of magnetic reconnection, we uncover another potential key to unlocking the origins of fast radio bursts. Magnetic reconnection occurs when magnetic field lines, tangled and twisted under extreme conditions, suddenly snap and realign. This explosive event releases vast amounts of energy in a fraction of a second, making it a prime candidate for generating the intense power observed in FRBs. In the context of neutron stars, magnetic reconnection could play a central role. These stars possess some of the strongest magnetic fields in the universe, and when these fields interact with surrounding matter, they can become highly unstable. As the magnetic field lines twist and break, the energy released could manifest as a fast radio burst, traveling across the cosmos at the speed of light. But it's not just neutron stars that might harness this process. Accretion disks around black holes or even the turbulent environments of magnetars could also experience magnetic reconnection, potentially producing FRBs as a result. The chaotic nature of these systems, combined with their immense magnetic fields, creates the perfect conditions for such dramatic energy releases. Scientists are particularly intrigued by the way magnetic reconnection could explain both the intensity and the brevity of FRBs. The sudden release of energy aligns closely with the millisecond durations observed in these bursts. Additionally, the process could account for the wide variety of FRB properties, as the conditions leading to reconnection can vary significantly between different cosmic environments. While magnetic reconnection is a compelling theory, it's not without its challenges. Understanding exactly how and where this process occurs in the universe requires precise observations and sophisticated modeling. Telescopes and detectors around the world are working to capture more data on FRBs, hoping to identify signatures that point directly to magnetic reconnection as the source. As research progresses, the role of magnetic reconnection in producing FRBs remains a promising avenue of exploration, offering yet another piece of the puzzle in our quest to understand these mysterious cosmic signals. Next, we'll delve into another dynamic force that could be at play: the role of shock waves in generating fast radio bursts. Now shifting our focus to the power of shock waves, we explore another intriguing possibility in the mystery of fast radio bursts. Shock waves are powerful disturbances that travel through space, often triggered by explosive cosmic events like supernova, neutron star collisions, or black hole mergers. These waves carry immense energy, capable of heating and accelerating particles to extreme speeds. Could they also be responsible for generating the brief but incredibly intense bursts of radio waves we detect as FRBs? One compelling scenario involves the aftermath of a supernova explosion. As the shock wave propagates through the surrounding interstellar medium, it interacts with magnetic fields and charged particles, potentially creating conditions ripe for FRBs. Similarly, when neutron stars collide, the resulting shock waves could disrupt magnetic fields and release bursts of energy in the form of radio waves. Another possibility lies in the interaction of shock waves with magnetars. These highly magnetized neutron stars are already considered prime suspects in the FRB mystery. If a shock wave passes through a magnetar's environment, it could trigger a sudden release of energy, manifesting as a fast radio burst. What makes shock waves particularly interesting is their ability to explain both the intensity and the variability of FRBs. The energy released in these events can vary greatly depending on the source and the surrounding environment, which aligns with the diverse properties observed in different FRBs. However, like all theories, this one faces challenges. Scientists need to gather more data to determine whether shock waves are indeed a significant source of FRBs. Observations of cosmic events that produce shock waves, combined with detailed modeling, could help confirm or rule out this hypothesis. As we continue to unravel the mysteries of FRBs, the role of shock waves remains a fascinating area of investigation, offering yet another piece of the puzzle in our quest to understand these enigmatic signals from the depths of space. Next, we'll turn our attention to the potential influence of supermassive black holes in the production of fast radio bursts. Now shifting our gaze to the colossal giants of the cosmos, we explore the possibility that supermassive black holes could play a role in the mystery of fast radio bursts. These behemoths found at the centers of galaxies are known for their immense gravitational pull and their ability to disrupt their surroundings in dramatic ways. But could they also be responsible for generating the brief, intense bursts of radio waves we detect as FRBs? One intriguing theory suggests that the chaotic environments around supermassive black holes might create the conditions needed for FRBs. As matter spirals into these black holes, it forms an accretion disk, a swirling ring of gas and dust heated to extreme temperatures. Within this disk, magnetic fields can become twisted and unstable, potentially releasing bursts of energy in the form of radio waves. Additionally, the powerful jets of particles that some supermassive black holes eject at near light speeds could interact with surrounding material, producing shock waves or other phenomena that might lead to FRBs. Another possibility lies in the tidal disruption events that occur when a star passes too close to a supermassive black hole. The star is torn apart by the black hole's gravity, releasing a tremendous amount of energy. Could this cataclysmic event trigger a fast radio burst? Observations of such events combined with radio telescope data could help scientists determine if there's a connection. What makes supermassive black holes particularly compelling in this context is their ability to generate enormous amounts of energy over vast distances. If they are indeed linked to FRBs, it could explain why some of these bursts originate from billions of light years away. However, this theory is still in its early stages, and more research is needed to understand whether supermassive black holes are a significant source of FRBs or if they merely contribute to the complexity of these signals. As we piece together the puzzle of fast radio bursts, the role of supermassive black holes adds another layer of intrigue, reminding us of the vast and dynamic processes at work in the universe. Next, we'll examine how the atmospheres of neutron stars might influence the production of these enigmatic signals. Now turning to the intricate details of neutron stars, we explore how their atmospheres might play a crucial role in the generation of fast radio bursts. Neutron stars are known for their extreme density and powerful magnetic fields, but their atmospheres are equally fascinating and potentially significant in the FRB mystery. The atmosphere of a neutron star is a thin layer of gas, often only a few meters thick, lying above the star's solid crust. Despite its thinness, this layer can reach incredibly high temperatures, sometimes exceeding 1 million degrees Celsius. Within this searing environment, electrons and ions interact in complex ways, creating conditions ripe for the production of intense electromagnetic emissions, including radio waves. Scientists theorize that disturbances in the neutron star's atmosphere, such as sudden temperature spikes or magnetic field fluctuations, could trigger the release of energy in the form of FRBs. One key factor is the interaction between the neutron star's magnetic field and its atmosphere. Neutron stars possess some of the strongest magnetic fields in the universe, and these fields can influence the behavior of particles in the atmosphere. For instance, magnetic reconnection, a process where magnetic field lines break and reconnect, can release vast amounts of energy. This energy might manifest as a burst of radio waves detectable across vast cosmic distances. Another possibility involves surface quakes on neutron stars. These quakes, caused by the star's crust adjusting to internal stresses, could send shock waves through the atmosphere, disrupting its delicate balance. Such disruptions might lead to the sudden emission of radio waves, potentially explaining some non-repeating FRBs. Additionally, the atmosphere's composition and density variations could influence how these bursts are shaped and propagated into space. While the role of neutron star atmospheres in producing FRBs remains speculative, it adds another layer of complexity to these cosmic puzzles. By studying the properties of these atmospheres and their interactions with the star's magnetic field, scientists hope to uncover more clues about the origins of FRBs. As we continue to probe the mysteries of these enigmatic signals, the atmospheres of neutron stars emerge as a critical piece of the puzzle, reminding us of the intricate and dynamic processes at play in the universe. Next, we'll delve into the similarities and differences between pulsars and FRBs, examining whether these two phenomena might be connected. Shifting our focus, let's examine the role of pulsars in the mystery of fast radio bursts and whether these two phenomena might be connected. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As these beams sweep across the cosmos, they create regular pulses of radiation detectable from Earth. This behavior has earned them the name cosmic lighthouses. At first glance, pulsars and FRBs share some striking similarities. Both involve neutron stars and emit intense radio waves, but there are key differences that set them apart. One major distinction lies in their timing. Pulsars produce highly predictable periodic signals, often pulsing at intervals ranging from milliseconds to seconds. In contrast, FRBs are sporadic and unpredictable, often appearing as single, milliseconds-long bursts, though some repeat irregularly. This unpredictability makes FRBs far more challenging to study and categorize compared to the clockwork precision of pulsars. Additionally, the energy released by FRBs can dwarf that of pulsar emissions, with some FRBs outshining entire galaxies in mere milliseconds. Another difference is their origin. While pulsars are well understood as rotating neutron stars, the exact sources of FRBs remain a mystery. Though some theories suggest that pulsars could produce FRBs under extreme conditions, such as during starquakes or magnetic field disruptions, there's no definitive evidence to confirm this link. Moreover, the vast distances to some FRBs billions of light-years away suggest they might originate from different cosmic environments than the relatively closer pulsars we observe in our own galaxy. Despite these differences, scientists continue to explore potential connections. One intriguing possibility is that certain types of pulsars, such as magnetized neutron stars with extraordinarily strong magnetic fields, could generate FRBs during violent outbursts. For example, in 2020, astronomers detected an FRB originating from a magnetar within our Milky Way, providing the first direct evidence linking these two phenomena. This discovery has fueled speculation that magnetars could be responsible for at least some FRBs, though it doesn't explain all cases. In summary, while pulsars and FRBs share some common traits, they remain distinct in their behavior, energy output, and origin. The hunt for a definitive link between them is ongoing, and each new discovery brings us closer to unraveling the secrets of these cosmic enigmas. As we continue our journey, we'll explore another fascinating angle: whether relativistic jets from black holes or neutron stars could produce FRBs. Now turning to the role of relativistic jets, we delve into another compelling theory behind the origins of fast radio bursts. Relativistic jets are powerful streams of particles ejected at nearly the speed of light from the vicinity of black holes or neutron stars. These jets are some of the most energetic phenomena in the universe, capable of stretching across vast cosmic distances. Could they also be the source of FRBs? One possibility is that these jets, when interacting with surrounding matter or magnetic fields, could produce the intense radio bursts we detect as FRBs. For instance, when a jet collides with interstellar gas or dust, it might create shock waves that generate short, intense bursts of radio energy. Similarly, magnetic instabilities within the jet itself could trigger sudden, powerful radio emissions. Another angle involves neutron stars. If a neutron star with a relativistic jet undergoes a sudden change, such as a magnetic field rearrangement or a collision with another object, the jet could release an FRB. This scenario would align with the sporadic nature of these bursts, as such events are unpredictable and rare. However, challenges remain in connecting relativistic jets to FRBs. While jets are known to emit radio waves, the exact mechanisms for producing the specific characteristics of FRBs, such as their extreme brightness and short duration, are still unclear. Additionally, the vast distances to many FRBs raise questions about whether the energy released by jets could travel so far and still remain detectable. Despite these uncertainties, the idea of relativistic jets as a source of FRBs is an exciting area of research. Each discovery, such as observations of jets in active galactic nuclei or around neutron stars, brings new insights. As scientists continue to study these jets and their potential links to FRBs, we may uncover clues that bring us closer to solving this cosmic mystery. With this theory in mind, we now shift our focus to another intriguing possibility, whether cosmic collisions could generate FRBs. As we shift our focus to the role of cosmic collisions, we explore another fascinating possibility in the quest to uncover the origins of fast radio bursts. Could these mysterious signals be the result of violent encounters between celestial objects? Cosmic collisions, such as those between neutron stars, black holes, or even massive asteroids, are among the most energetic events in the universe. These collisions release enormous amounts of energy, often in the form of gravitational waves, light, and other radiation. But could they also produce FRBs? One compelling theory suggests that when two neutron stars collide, the immense forces involved could generate a powerful radio burst. Such events are rare and short-lived, which aligns with the sporadic and brief nature of FRBs. The collision could create shock waves or magnetic instabilities that result in a sudden, intense radio emission. Additionally, the merging of neutron stars often leads to the formation of a black hole or a highly magnetized neutron star, both of which could continue to produce energetic phenomena like FRBs. Another scenario involves the collision of a black hole with a neutron star. As the black hole tears apart the neutron star, the intense gravitational forces could eject material at near light speeds, potentially triggering an FRB. Similarly, collisions between massive asteroids or other dense objects in space could generate shock waves capable of producing short-lived radio bursts. While these events are less energetic compared to neutron star mergers, they could still contribute to the FRB phenomenon. However, linking cosmic collisions to FRBs is not without challenges. While these collisions are known to produce gravitational waves and other forms of radiation, direct evidence connecting them to radio bursts is still limited. Additionally, the immense distances to many FRBs raise questions about whether the energy released in such collisions could travel so far and remain detectable. Despite these uncertainties, the idea remains an intriguing area of research. As scientists continue to study cosmic collisions and their potential links to FRBs, each discovery brings us closer to understanding these enigmatic signals. Whether it's the merger of neutron stars or the collision of black holes, these cosmic events may hold the key to unraveling one of the universe's greatest mysteries. With this theory in mind, we now turn our attention to another speculative idea whether quantum tunneling could play a role in the generation of FRBs. As we venture into the realm of quantum physics, a new and intriguing possibility emerges in the quest to understand fast radio bursts. Could quantum tunneling, a phenomenon that defies classical physics, be involved in the generation of these cosmic signals? Quantum tunneling occurs when particles pass through energy barriers that, according to traditional physics, should be impossible to overcome. This process is well documented in microscopic systems, such as electrons moving through semiconductors, but could it also play a role on a cosmic scale? One theory suggests that quantum tunneling might occur in the extreme environments surrounding neutron stars or black holes. In these regions, the intense gravitational and magnetic fields could create conditions where particles escape confinement through tunneling. For example, in the magnetosphere of a neutron star, charged particles trapped in magnetic fields might tunnel out, releasing energy in the form of a radio burst. This could explain the sudden and intense nature of FRBs, as tunneling events are inherently quick and unpredictable. Another possibility involves the quantum behavior of matter in the cores of neutron stars. The extreme pressure and density in these environments could lead to exotic states of matter where quantum effects dominate. If particles within the neutron star core tunnel through energy barriers, the resulting energy release could be channeled into a powerful radio burst. This would align with the idea that FRBs originate from highly energetic and compact objects. However, linking quantum tunneling to FRBs remains highly speculative. While the phenomenon is well understood in laboratory settings, applying it to cosmic scales presents significant challenges. The distances and energies involved in FRBs are vastly different from those studied in quantum physics experiments. Additionally, the mechanisms by which tunneling could produce a coherent radio burst are not yet clear. Despite these uncertainties, the idea of quantum tunneling contributing to FRBs opens up exciting new avenues for research. It challenges scientists to think beyond classical astrophysics and consider the potential role of quantum effects in shaping the universe's most energetic phenomena. As we continue to explore this theory, we move closer to uncovering the full story behind fast radio bursts. With this in mind, we now shift our focus to the role of neutron star magnetic fields in generating these mysterious signals. Now shifting our gaze to the immense magnetic fields of neutron stars, we uncover another layer of the fast radio burst mystery. Neutron stars, the remnants of massive stars after supernova explosions, are some of the most magnetic objects in the universe. Their magnetic fields are billions of times stronger than Earth's, creating environments where extraordinary physical processes can occur. But how could these magnetic fields generate the intense bursts of radio waves we detect as FRBs? One key idea centers on the concept of magnetic reconnection, a process where magnetic field lines break and reconnect, releasing vast amounts of energy. In the extreme environment of a neutron star, this reconnection could occur in the magnetosphere, the region dominated by the star's magnetic field. When magnetic field lines snap and realign, they accelerate charged particles to nearly the speed of light, producing a burst of electromagnetic radiation. This sudden release of energy could manifest as a fast radio burst, explaining the immense power packed into such a short signal. Another possibility involves the twisting and snapping of magnetic field lines due to the neutron star's rapid rotation. As the star spins, its magnetic field can become tangled and strained. When these field lines eventually snap, they release energy in the form of radio waves. This process, known as a magnetic flare, could also account for the sporadic and unpredictable nature of FRBs. Additionally, the intense magnetic fields could channel and focus the released energy into a narrow beam, amplifying the signal and making it detectable across vast cosmic distances. However, the connection between neutron star magnetic fields and FRBs is not without its challenges. While magnetic reconnection and flares are well-studied phenomena, the exact mechanisms that would translate these processes into coherent radio bursts are still unclear. Moreover, the extreme conditions near neutron stars make it difficult to observe these events directly, leaving scientists to rely on theoretical models and indirect evidence. Despite these uncertainties, the role of neutron star magnetic fields in producing FRBs remains a compelling area of research. It highlights the incredible power of these cosmic objects and the complex interplay between magnetic fields and high-energy astrophysical phenomena. As we continue to explore this theory, we gain a deeper appreciation for the forces shaping the universe's most enigmatic signals. With this in mind, we now turn our attention to the speculative idea that exoplanets might be involved in the production of fast radio bursts. Now venturing into a fascinating and speculative realm, let's consider whether planets outside our solar system could play a role in the production of fast radio bursts. While this idea may seem far-fetched at first, it opens up intriguing possibilities for understanding these cosmic signals. Could exoplanets, with their diverse environments and interactions with their host stars, contribute to the creation of FRBs in ways we haven't yet imagined? One theory suggests that exoplanets orbiting neutron stars or magnetars might be key players. Imagine a planet in close orbit around a highly magnetized neutron star. The intense tidal forces and magnetic interactions between the planet and the star could lead to dramatic events. For instance, if the planet's atmosphere were stripped away by the star's powerful magnetic field, the resulting plasma could interact with the star's magnetosphere, potentially triggering a burst of radio energy. This process, though hypothetical, could explain how exoplanets might indirectly produce FRBs. Another possibility involves the collision or disruption of exoplanets in dense star systems. In regions where stars are packed closely together, gravitational interactions could fling planets into chaotic orbits, leading to collisions or close encounters. If a planet were to collide with a neutron star or be torn apart by its gravitational forces, the resulting debris and energy release might generate a fast radio burst. Such catastrophic events would be rare but could account for some of the sporadic FRBs we detect. Interestingly, exoplanets with strong magnetic fields of their own could also play a role. If a planet's magnetic field interacts with that of its host star, it might create conditions for magnetic reconnection, a process we've already explored as a potential source of FRBs. The energy released during these interactions could manifest as a brief but intense burst of radio waves, adding another layer to the mystery. Of course, the idea of exoplanets contributing to FRBs remains speculative, and there's little direct evidence to support it. However, as the study of exoplanets continues to advance, and as we discover more about their diverse properties and interactions, this theory could gain traction. It serves as a reminder of how interconnected the cosmos is, and how seemingly unrelated phenomena might be linked in surprising ways. As we wrap up this exploration, it's clear that the role of exoplanets in FRB production is an area ripe for further investigation. While it's just one piece of the puzzle, it highlights the boundless creativity of scientists as they seek to unravel the mysteries of the universe. With this in mind, we now turn to the broader question of how the evolution of the cosmos itself might shape the frequency and nature of fast radio bursts. As we shift our gaze to the grand tapestry of cosmic evolution, let's explore how the universe's ongoing transformation might shape the enigmatic fast radio bursts. The universe is not static, it's a dynamic, ever-changing expanse, and its evolution could hold clues to the behavior and frequency of these mysterious signals. The expansion of the universe, driven by dark energy, plays a significant role in shaping the conditions under which FRBs occur. As the universe stretches, the distances between galaxies and cosmic objects grow, altering the environments in which FRBs are born. For example, in the early universe, galaxies were closer together, and interactions between stars, neutron stars, and other celestial bodies were more frequent. This could have led to a higher rate of FRB production in the past compared to today. As the cosmos continues to expand, these interactions become rarer, potentially explaining why some FRBs seem to originate from vast distances and why they are such fleeting events. Another factor to consider is the life cycle of stars and galaxies. Over billions of years, stars are born, evolve, and die, leaving behind remnants like neutron stars, black holes, and white dwarfs. The distribution and density of these objects have changed over time, influencing where and how FRBs might occur. In the early universe, the abundance of massive stars meant that neutron stars and black holes' potential FRB sources were more common. As these stars exploded in supernova, they seeded the cosmos with the ingredients for future FRBs. Today, the universe's stellar population is different, with fewer massive stars but more evolved remnants, which could affect the frequency and characteristics of FRBs. Cosmic evolution also impacts the environments in which FRBs propagate. The interstellar medium, the space between stars, has evolved over time, becoming less dense and more diffuse as the universe expands. This change affects how FRB signals travel and how they are observed here on Earth. For instance, FRBs from the early universe might have encountered denser plasma, causing their signals to be more distorted or delayed by the time they reach us. Understanding these effects could help scientists decode the origins and properties of FRBs more accurately. Finally, the universe's evolution influences the tools we use to study FRBs. As technology advances and our understanding of the cosmos deepens, we're able to detect and analyze FRBs with greater precision. Telescopes like the Square Kilometre Array, set to become operational in the coming years, will allow us to observe FRBs in unprecedented detail, shedding light on how cosmic evolution has shaped these signals over time. In summary, the evolution of the universe is more than just a backdrop to the mystery of FRBs, it's an active participant. From the changing density of stars and galaxies to the expansion of space itself, cosmic evolution influences where, when, and how FRBs occur. As we continue to explore these connections, we gain a deeper appreciation for the intricate interplay between the universe's history and the enigmatic phenomena it produces. Now, let's turn our attention to one of the most intriguing questions in the study of fast radio bursts. Could the spin of neutron stars be the key to generating these mysterious cosmic signals? Neutron stars are already known for their extreme properties, from their incredible density to their powerful magnetic fields. But their rapid rotation adds another layer of complexity to the puzzle. Neutron stars can spin at astonishing speeds, with some completing hundreds of rotations per second. This rapid spin converts their immense rotational energy into other forms, including electromagnetic radiation. Scientists have theorized that this spinning motion could create the conditions necessary for FRBs to occur. For example, as a neutron star spins, its magnetic field twists and shifts, potentially releasing bursts of energy in the form of radio waves. These bursts could align with the characteristics we observe in FRBs: intense, brief, and highly energetic. One specific mechanism tied to neutron star spin is the magnetic reconnection process. As the star rotates, its magnetic fields can become tangled and then suddenly snap back into place, releasing a massive amount of energy in the process. This sudden release could produce the short, bright flashes we detect as FRBs. Additionally, the spin of a neutron star could influence how often these events occur. Faster spinning neutron stars might produce more frequent bursts, while slower ones could generate them more sporadically. Another factor to consider is the interaction between a neutron star's spin and its surrounding environment. For instance, if a neutron star is part of a binary system, its spin could be influenced by its companion star. This interaction might lead to periodic bursts or even repeating FRBs, like the famous FRB 121102. The star's spin could also affect how its magnetic field interacts with nearby plasma or other cosmic material, shaping the properties of the FRBs it produces. Interestingly, the spin rate of a neutron star isn't constant, it changes over time. Young neutron stars tend to spin faster, but as they age, they slow down due to the loss of rotational energy. This evolution could explain why some FRBs are more common in specific regions of the universe or at certain points in cosmic history. For example, in the early universe, when neutron stars were younger and spun faster, FRBs might have been more frequent. Today, as neutron stars age, their slower spin rates could contribute to the rarity of these bursts. While the idea that neutron star spin plays a role in FRBs is compelling, it's important to note that this is still a developing area of research. Scientists are actively studying the connection between spin rates and FRB production, using both theoretical models and observational data. Telescopes like the Square Kilometre Array and the Canadian Hydrogen Intensity Mapping Experiment are expected to provide new insights into this relationship, helping us understand whether spin is indeed a driving force behind these cosmic enigmas. In summary, the spin of neutron stars offers a fascinating avenue for exploring the origins of fast radio bursts. From magnetic reconnection to interactions with their environments, the rotation of these dense stellar remnants could hold the key to unlocking one of the universe's greatest mysteries. As we continue to investigate, the answers we uncover will not only deepen our understanding of FRBs, but also shed light on the extraordinary physics of neutron stars themselves. Now shifting our focus to another compelling piece of the fast radio burst puzzle, let's delve into the role of plasma instabilities in these cosmic signals. Plasma, often referred to as the fourth state of matter, is a hot, ionized gas that permeates much of the universe. It's found in stars, in the space between stars, and even surrounding galaxies. But how could this chaotic, electrically charged material contribute to the creation of FRBs? One key concept is that plasma is highly dynamic and prone to instabilities. These instabilities occur when the balance of forces within the plasma is disrupted, leading to sudden and dramatic changes in its behavior. For example, when magnetic fields within the plasma become twisted or stretched, they can snap and release bursts of energy. This process, known as magnetic reconnection, is one way plasma instabilities could generate the intense, short-lived bursts we observe as FRBs. Another possibility involves turbulence within the plasma itself. Turbulence occurs when chaotic motions and interactions within the plasma create fluctuations in density, temperature, and magnetic fields. These fluctuations can amplify certain waves or oscillations, potentially leading to the release of radio waves. In some cases, this amplified energy could manifest as an FRB. Scientists believe that such turbulence could occur in environments like the magnetospheres of neutron stars or the regions around black holes, where conditions are extreme and highly energetic. Plasma instabilities could also play a role in the propagation of FRBs through space. As these bursts travel across the universe, they pass through vast clouds of plasma. Interactions between the FRB signal and the plasma can cause distortions such as scattering or dispersion, which affect how the signal is detected on Earth. By studying these distortions, scientists can learn more about the properties of the plasma the FRBs encountered, as well as the environments they originated from. Interestingly, certain types of plasma instabilities could explain why some FRBs repeat while others do not. For instance, if a region of plasma undergoes cyclical instabilities, where disruptions build up, release energy, and then rebuild, it could produce repeating bursts. On the other hand, a one-time instability in a specific region might result in a single, non-repeating FRB. This variation could help explain the diversity of FRB behavior observed by astronomers. While the idea of plasma instabilities as a source of FRBs is promising, it's still an area of active research. Scientists are using computer simulations and laboratory experiments to better understand how these instabilities behave and whether they can indeed produce the intense radio bursts we detect. As our knowledge of plasma physics grows, so too does our ability to unravel the mysteries of FRBs and the cosmic environments that give rise to them. In exploring the role of plasma instabilities, we're reminded just how interconnected the universe's most extreme phenomena are. From the turbulent gas of distant galaxies to the magnetic fields of neutron stars, these cosmic puzzles continue to inspire and challenge our understanding of the cosmos. And with each discovery, we move closer to answering one of space's most tantalizing questions: what exactly are fast radio bursts? Now shifting our gaze to another fascinating aspect of neutron stars, let's explore how their cooling process might be connected to the enigmatic fast radio bursts. Neutron stars, the dense remnants of massive stars that have gone supernova, are some of the hottest objects in the universe at their birth, but over time they gradually cool down, radiating their immense heat into space. This cooling process is not just a slow fade, it's a complex phenomenon that could have dramatic consequences, including the generation of FRBs. As a neutron star cools, its internal structure undergoes significant changes. The star's core, composed of ultra-dense matter, loses heat primarily through neutrino emissions and to a lesser extent through thermal radiation. During this cooling phase, the star's crust and magnetic field can experience shifts and instabilities. These changes might trigger sudden releases of energy, potentially manifesting as the intense radio bursts we observe as FRBs. Some theories suggest that cracks or starquakes in the neutron star's crust, caused by the cooling and contraction of the star, could release bursts of radio waves. Another intriguing possibility is that cooling affects the behavior of the neutron star's magnetic field. Neutron stars possess some of the strongest magnetic fields in the universe, and as the star cools, these fields can become more volatile. Magnetic reconnection events, where magnetic field lines break and reconnect, could release enormous amounts of energy in the form of FRBs. Additionally, the cooling process might influence the alignment or strength of the magnetic field, creating the right conditions for a burst to occur. Interestingly, the cooling rate of neutron stars varies depending on their age, mass, and internal composition. Younger neutron stars cool more rapidly, while older ones take longer to lose their heat. This variation could explain why some FRBs appear to originate from younger, more energetic neutron stars, while others might come from older, slower cooling ones. By studying the cooling rates of neutron stars, scientists can gain insights into the timing and frequency of FRBs, potentially linking specific bursts to particular stages in a neutron star's life. While the idea of neutron star cooling as a source of FRBs is compelling, it's still a hypothesis that requires further investigation. Observations of neutron stars at different stages of cooling, combined with theoretical models, will be crucial in determining whether this process plays a significant role in producing FRBs. As our understanding of neutron star physics advances, we may uncover even more connections between these cosmic powerhouses and the mysterious bursts of radio energy they might generate. With each step forward, we're reminded of the intricate dance of forces that shape the universe. From the cooling cores of neutron stars to the fleeting brilliance of FRBs, these cosmic phenomena continue to challenge and inspire our quest for knowledge. And as we unravel their secrets, we come closer to understanding the true nature of these enigmatic signals. As we look ahead to the future of fast radio bursts research, the possibilities are both exciting and boundless. New advancements in technology and theory are paving the way for deeper insights into these mysterious cosmic signals. One of the most promising developments is the rise of next-generation radio telescopes, such as the Square Kilometre Array, or SKA. With unprecedented sensitivity and resolution, This global collaboration of telescopes will allow scientists to detect and study FRBs with far greater precision than ever before. By capturing more data on these bursts, researchers can begin to piece together their origins and behavior. In addition to cutting-edge telescopes, improvements in computational power are transforming how we analyze FRBs. Advanced algorithms and artificial intelligence are being used to sift through vast amounts of data, identifying patterns and anomalies that might have gone unnoticed. These tools not only speed up the process of discovery, but also open up new avenues for understanding the complex physics behind FRBs. For instance, machine learning models are helping scientists simulate the environments where FRBs might originate, providing valuable clues about their sources. Theoretical advancements are also playing a crucial role in unraveling the mysteries of FRBs. New models of neutron stars, black holes, and other cosmic phenomena are being developed to explain how such immense bursts of energy could be generated. Some researchers are even exploring the possibility that exotic objects like quark stars or cosmic strings might be involved. As these theories evolve, they offer fresh perspectives on the nature of FRBs and their place in the cosmos. Another exciting frontier is the study of FRBs in conjunction with other cosmic events, such as gravitational waves or gamma-ray bursts. By observing these phenomena together, scientists can gain a more comprehensive understanding of the universe's most energetic processes. For example, if an FRB is detected simultaneously with a gravitational wave, it could provide direct evidence linking these signals to neutron star mergers or other cataclysmic events. Collaboration is also key to the future of FRB research. Astronomers, physicists, and engineers from around the world are joining forces to share data, resources, and insights. This global effort ensures that no stone is left unturned in the quest to understand FRBs. Moreover, citizen science projects are engaging the public in the search for these signals, turning amateur astronomers into valuable contributors to the field. As we continue to push the boundaries of our knowledge, one thing is certain: the study of FRBs is far from over. With every new discovery, we come closer to unlocking the secrets of these enigmatic signals and, by extension, the universe itself. The future of FRB research promises not only to answer the questions we have today, but also to raise new ones, driving our exploration of the cosmos ever forward. And as we stand on the brink of these new horizons, we're reminded that the universe is full of wonders waiting to be uncovered. As we bring our exploration of the 50 mysteries of fast radio bursts to a close, one thing is undeniable: these cosmic signals are as fascinating as they are perplexing. From their mysterious origins to their immense energy, from their repeating patterns to their vast distances, FRBs continue to challenge our understanding of the universe. Each mystery we've uncovered only deepens the sense of wonder surrounding these fleeting bursts of radio waves, reminding us of how much there is still to discover. The journey to unravel the secrets of FRBs is far from over. With every new observation, every technological advancement, and every groundbreaking theory, we move closer to piecing together the cosmic puzzle they represent. But even as we make progress, the universe seems to have a way of presenting us with new questions, keeping us in awe of its infinite complexity. Now it's your turn to join the conversation. What do you think causes these enigmatic signals? Could they be the result of natural cosmic phenomena, or is there a more extraordinary explanation waiting to be uncovered? Share your thoughts and theories in the comments below. We'd love to hear your ideas and continue this journey together. And if you're as captivated by the mysteries of the cosmos as we are, don't forget to subscribe and hit the notification bell. There are countless more wonders of space to explore, and we can't wait to take you with us on the next adventure. Until then, keep looking up. The universe is full of surprises.